Next talk is by Robert Monjo from the Complutense University of Madrid in Spain, and he's going to be talking about beyond the standard model from coasting cosmology to MOND-like gravities. So, Robert, whenever you want.
Yes, as mentioned by Elena, this is an attempt to be beyond the standard model and show some clues about the linear expansion or coasting cosmology that Moncy John will explain later, and the MOND-like gravities as mentioned before. The idea is to check the principles of the cosmology, to review the most important base of this standard cosmology. As you know, we have a lot of problems, like the Hubble tension, the nature of dark matter and dark energy is not well explained by a standard model, and we need to introduce new parameters for explaining this tension, like the early dark energy or the dynamical dark energy, and more and more parameters to solve all the current issues of the standard model, like the overfitting of the epicycles for the well-known Ptolemy model in astrophysics. So I am putting the attention to the synchronicity problem, that the age of the universe is very close to the Hubble time, with statistical compatible in most observation, maybe Planck with some tension, and the coincidence that the expansion now is very approximately to the one universe without energy, without matter. So empty universe and our universe are expanding in a similar way. The question is why we have these coincidences. Also, all the observation seems to point that universe is flat, and a lot of observational issues as mentioned before, but also theoretical issues, the flatness problem, the horizon problem, the infinity problem. Can a singularity expand to an infinite flat in an finite time, for a finite speed, like the light speed? And one interesting theoretical issue is the embedding problem. Why is separately embedded the spatial section and the factor scale? That is, my concern is that the Freeman-Lemaitre-Robinson Walker metric is artificially built with two steps. First, the spatial part is statically embedded in a spatial Riemannian spatial flat, and after this the scale factor is added, and the time is fixed with lapse equal to 1, and this is not natural in terms of geometrical embedding, because we are in a Lorentzian manifold. So we need to use dynamical embedding instead of the statical embedding. Well, as you know, we have two geometrical perspectives: the intrinsic, used in Riemannian geometry and pseudo-Riemannian geometry, and the classical extrinsic perspective, used in, for example, in 3 dimensions, but also is valid for Lorentzian and Riemannian manifolds. And the idea is to compare our vision of the universe with the geometrical approach to the dynamical embedding of Lorentzian manifolds. The idea is to test some easy manifolds, for example, the hypercon with positive spatial section, the equivalent for the negative spatial curvature, and the flat. And using that the space-time is a dynamical system, so we can apply Euler-Lagrange equations to test analytically how is the behavior. And using the moving reference frames from observers, the metric, the spatial section is suffering an inhomogeneity, a radial inhomogeneity. This is fictitious. This is from the point of view of the observer, and this radial inhomogeneity can be assimilated within a flat homogeneous space as an acceleration. So using adequate stereographic projection, the manifold, the space-time manifold, can be apparent, infinite, and accelerated. So with this approach of embedding the hypercon with positive, negative, or flat, we obtain an alternative metric to the Feynman-Lemaitre-Robinson-Walker that has the same spatial section, but the scale factor is linear with linear expansion, and we have two additional terms: the shift and the lapse. With a lapse and shift, if we change the coordinates, we obtain a radial inhomogeneity metric spatially, but locally for each point, this is homogeneous, and the resulting Ricci scalar is this one. And taking, for example, positive curvature, the Ricci scalar or our positive curved spacetime is the same that the standard model when it is flat and linear expanding. So our model of spherical expanding hyperspheres are equivalent to the flat standard model with linear expansion. So this is the Méliès model. And applying the Lagrangian formalism and the Hamiltonian equations of and now with the Misner formalism, we obtain that our manifold is only consistent with positive curvature. That is an three-sphere expanding at like speed, and the equivalent density, taking into account the Ricci scalar, is exactly the critical density. And also this is, as popularly mentioned before, as a black hole, that the escape speed is the light speed. So is a very nice coincidence, and is the only one, the unique solution from the Hamiltonian equations. And comparing with observations, the luminosity distance is constrained the model in the same statistical level than the standard model, and is better than the flat coasting model and the Milner coasting model. comparing to the angular diameters is similar to the standard model. Also for the cosmic chronometers, the results of the Hubble parameter are similar, but with two perspectives, the intrinsic and the extrinsic, because the hyperconical model can be analyzed in extrinsic view, in which the Hubble parameter is just the inverse of the age of the universe. Intrinsically is simulated and visual acceleration. And applying the perturbation theory, it's possible to apply also the fictitious acceleration at galactic scale, and is assimilated as a Milgrom-Mean acceleration. So the MOND behavior can be recovered with this fictitious acceleration, like the Coriolis acceleration in the atmosphere. And this acceleration, without using observation, is predicted to be very similar to the standard model dependent observation, and with two different values at local and at global. So we can simulate and Hubble tension according to purely geometric techniques, obtain a Hubble that is the inverse of the age of the universe, will intrinsically the prediction of the Hubble parameter is very similar to the lambda CDM dependent observation. As conclusions, we have two geometrical perspectives, an homogeneous hypercone expanding to the at light speed is assimilated as a projected radial inhomogeneity that is apparently accelerated flat metric, like the Melias metrics. And these fictitious accelerations is assimilable to dark matter and dark energy, predicting specific values, apparent values, and also in galaxies and galaxy curve rotation. And possible explanation of the Hubble tension with difference in the local and global scales. I don't know if the local void is an apparent of current time, because the differences in distance is also in time. So maybe it's linked. I don't know. I'm not sure. And an explanation for the critical density and for the galactic, also summarizing that is as two perspectives, modeling the most promising models as alternative of the standard model. This is all from my side.
Can you go to slide 11 with the different table of the different values of the H naught?
Yes,
yeah, exactly.
The three parameters are our model, and the second part of the table is is predicted for the standard.
Predicted based on the model, I see. So what I was wondering is, like, the local value is about 74. I don't see that in this table, but can you how do you explain the race observations of supernovae in the local H naught, basically?
Yes. The local prediction for dark energy is 0.67,
Yeah,
and
but for the H
dark matter plus. Yes.
No, yeah, that's interesting. So the omega m should be exactly 1/3, and omega lambda is 2/3, which is it's quite reasonable. But what about for the H naught?
So, sorry, can you repeat the question? Is about the
it's about the last line of this table, right?
The last line. The last line is a prediction for the Hubble, and the previous one is the prediction for the time the comparison with the age of universe and the Hubble time within the intrinsic viewpoint.
Yeah, but okay, so the age of the universe is a different issue, which I haven't asked about yet. But what I was asking about is how do you explain the high local value of H naught observationally? So that it's about 74, right? If you were to do a local measurement.
Okay. Do you mean about this habit? Yes, because it depends of the technique. This local value is from
Yeah.
lambda CDM, and
Hang on, I thought you
the
said just
local
now that
value
all the
from
values were predicted based on
the
epsilon, delta, and alpha.
the observation with purely geometrical techniques
Oh,
is just the inverse of time. So our prediction is this one. One moment. 73 for local measurements within the extrinsic viewpoint. That is
right.
purely geometrical techniques as laddering of supernovae compared to the for example, one moment. No, our prediction is this one, and this is the observation from Rees. Sorry, from Rees et al.
So
This
you're in
is the
agreement
observation
with that.
73. Yes, and our prediction based on the age of very low metal stars is 73 with instantly, but using the edge universe from lambda CDM is 72. So
Okay.
we distinguish between geometrical techniques and observation depends of the light
Yes, sure.
of the light features.
Just one quick thing I wanted to ask: how exactly is this FT defined? FT, the second last line. How exactly is that defined?
FT, yes, FT is the quotient between the predicted time and the Hubble time.
So it's the age of the universe multiplied by H naught.
Yes, yeah, exactly. This is as this feature this
So
FT.
just one quick question. How old? Okay, so the universe is basically. How old exactly is this? So it's like 4% less than the inverse of H naught. Is that what you're saying?
Yes, I think that we can reproduce the observation of Planck according to this fictitious acceleration.
Sorry,
Without a
Planck
fictitious
is an observation.
acceleration,
The Planck doesn't directly tell you the age of the
yes,
universe. What I
yes,
was saying is like, if you get an age between 13.5 and 14 gigayear, because
yes. The
because you can't use Planck to
difference is
determine the
of
age of the
yes,
universe. You have to do that from like stellar stars or globular
yes.
clusters, right? But I think you're consistent with that bound, right? That
Is uh, uh, this is from the integral. One moment. Uh,
yeah, you'd have to do some sort of integration to find the
this,
age of the universe, right? But it
yes,
seems
yes,
like it would be
the definition of the with
so. I was just wondering, like, if you haven't figured it out now, that's fine. But I was just wondering, like, so you get an age between like 13.5 and 14 gigayear, right? If you with your cosmology, right?
yes, yes, yes.
Okay, then it should be reasonable given like non-cosmological constraints on the age of the universe. That's all I wanted to ask for now.
This only is predicting the factor, not the exact value of the
Yeah, but
age.
obviously, if you were to multiply the factor by,
Yes,
you were to do FT divided by H naught, you could. I would suggest like maybe adding another row, which is like the predicted age of the universe in gigayear.
of course, this is independent of the time. We always predict that the apparent dark energy is 0.7,
No, I understand. Like,
0.70, and also always we predict this factor, and so this is from the coincidences of the linear expansion, the synchronicity problem. So it's
You mean the
easy
fact that
to predict.
so you mean the fact that the expansion history is very close to linear?
Yes.
Yeah. Okay.
So always we have this problem is if the synchronicity problem is true, that always is apparently linear, we can predict this one. The differences of 4-5% is due to the assimilation of the fictitious acceleration from the radial inhomogeneity, of the moving observers, and produce an apparent the differences in the past from this distorting curvature from each observer, but it's fictitious. So each observer observe the same phenomenon of apparent acceleration in the past.
I think Morris had a question. Maybe that can be the next one.
Yeah, I have maybe
Yes, okay.
2 questions, but they're all related. What do you predict for the future state of the universe? Theoretically, this is relevant because in lambda CDM, as you know, that's a stable de Sitter state. Do you predict the same?
The prediction is like this, is linear. So the values expected for apparent dark energy and dark matter will be the same in the future. The differences are in the local structures, but in this case we did not simulate the local structures, but I think it's possible. So the prediction of the universe is a costing universe with always expanding, always expansion, and is easy. And I don't know if is the answer for your question.
Because well, you're also sketching linear expansion, and of course for linear expansion, the deceleration parameter will be 0, and that's certainly not supported by the data.
Yes, because
I mean, it's in the wrong.
It's from the extrinsic viewpoint. The extrinsic viewpoint is linear and acceleration 0. But according to the intrinsic viewpoint, there is an fictitious acceleration. The dynamical embedding is due to the moving reference frames. The observer is also expanding with the universe. So luminosity distance is not like this. It's not like the extrinsic viewpoint. We are suffering an radial inhomogeneity in the lapse and the shift terms of the metric. And this inhomogeneity is very similar, is exactly equal to an apparent acceleration. So the acceleration observed by the co-moving observers is fictitious according to the dynamical embedding.
Well, fine, but what would the observer see then if the observer measures Q0?
Yes. So we need to distinguish between directly observations and indirect observations. The direct observations are with purely geometric techniques. For example, the laddering of supernova stars and the directly evolution of the clusters. But the luminosity distance and other measurements of the light are affected by this fictitious acceleration, because light is moving on the geodesics of this one. So observations based on light are not valid for view the extrinsic viewpoint, but the evolution, the cosmic timeline, yes, cosmic timeline will be always linear. That is the synchronicity problem, and the age of the galaxies, the age of the evolution of the structures will be also linear. So we can explain the tensions of the Gordo, of the bigger structures, thanks to this linear expansion and the MOND behavior inherited from this fictitious acceleration. So it's possible to falsify this model according to the cosmic timeline that will be specifically the inverse of time or inverse of age of the universe.
Okay, thank you.
Well, it would be nice if you can give a number for Q0 that, you know, the observer would
yes.
measure, say, based on supernovae.
And you can read these more questions?
I think Pavel also has a question.
Yes, you mentioned that this approach leads to a MOND-like behavior, right? So I imagine you are probably thinking that it will be flat rotation curves, right? That's interesting. Down to which scale would you? I mean, would open star clusters look Mondian in this approach? So on a scale of a parsec, you think?
I not check every details, but the scale is shown here in the rate of escape velocity and Hubble rate, Hubble speed, and the empty universe is in this region, and the black holes, for example, is in this asymptotic in this parameter 0.5. So all observations we analyze is between, and we need to check specifically how is happening in your region. But the idea is that the phenomenology depends only the acceleration, not from the scale, because it's a problem of dynamical systems or the velocities. It's not a problem of space. It's a problem of the rate of speeds. So we need to focus on the dynamical and not in the scale, in my opinion.
Well, sure, MOND is an issue of acceleration. I agree, but we see MOND effects in open star clusters, and the question is whether well, you would have to also show that would be possible in this formulation, right?
Yes.
So
I think we can check in the future. Yes, thank you.
Sure. Great. Thanks.
Okay, thanks. I think Andrini also has another question.
So related to this, did I understand correctly on this slide that gamma m over pi would, for a very small system with a low ratio of escape velocity to, so would star clusters be on the left of this plot then, at a very low ratio of V over V8?
Yes.
Okay, so
yes.
that means
so
that
this is
gamma...
the Milgronian acceleration is not constant in this model. Depends of the scale of the dynamical scales. That is,
So what you're saying is that gamma m
the
over pi
empty,
would be about 0.35?
yes, for the empty universe is 0.33, and for black
So
holes is 0.5. This, so the Milgramian acceleration is 0 for black holes.
But at the okay, yes, at the right end, because gamma m would be half pi.
So a star cluster being about a parsec large. On the parsec, the Hubble rate is extremely small, right?
Yeah.
And so the escape speed is also small, but that's around maybe kilometers per second. So I think you would be on the right.
But the VE is much lower than VH though, because the Hubble rate is oh sorry, no, it's the other way around.
Yeah, but the Hubble rate is on that scale, right? So the Hubble VH
Hubble rate on that scale is very tiny, actually.
Yeah, exactly.
So does
I have a problem because our theory predicts the gray line.
Yes, okay.
And the observed one is the blue. So I don't know why is this difference, but the behavior is very similar. So maybe we need to review the theory in the future, but we are glad because it's possible to adjust the theoretical one to the empirical to obtain the observation. But it's a curiosity why we predict without observations this behavior for black holes 0.5, and the smallest scale galaxies is not exactly passing throughout this gray line, but we will need check in the future. Yes.
So my question was actually not related to this. What I was asking is for the galaxy scales regarding the A0 parameter or the effective value of A0 that you predict, which I guess is
Galaxy scale is this one, and cluster I think is this one.
Okay, so and the galaxy scale in like meters per second squared, how much are you predicting for the value of A0?
We need to check exactly if you want after this talk.
Okay, fair enough.
Because
what another thing I wanted to ask is like regarding the time evolution of A0. Did I understand correctly that that the A0 will be proportional to 1 over A in the model? It'll be inversely proportional to the scale factor. Is that right?
Yes, the scale factor. But we need to yes, one moment here. No, here. But important thing.
Yeah.
This is a metric with lapse and shift. So if we include this shift and lapse in only dependent spatial and time, so that is removing this part, the linear expansion is appearing as an fictitious acceleration. So is linear expansion in terms of extrinsic viewpoint, but assimilating this in radial homogeneity is pseudo accelerating.
No, but I meant like if you think about an observer at low redshift who's looking at a galaxy at redshift 1, then it's so you can use rotation curves to try and get like constraints on the value of A0 at that epoch, right? And typically that implies that A0 shouldn't have risen faster than a to the minus 3 halves as you go back into the past. But so if you're predicting a rise going as a to the minus 1, that should be reasonable.
Yes, and the problem is the information that arrive from light, because it's distorted. So it's a problem. We need to separate the information from the light and information from the phenomenon, from the cosmic timeline.
Yeah, but I think you already explained that like the overall age of the universe in your model is more or less reasonable. So
if there are no more questions, maybe we could just do the break now if there are no more questions.
Yes.
Okay.
Yes, thank you very much.